Okay, so now let's talk about it's probably only non-number theoretic corollary, which is any measurable subset of R with positive measure contains a non-measurable subset. So, okay, let's recall the following definitions before we give a detailed proof. So, okay, let's recall the definition of the Vitali set V. So we consider the following equivalence relation. If the two real numbers are similar, if and only if their difference is rational. And its quotient set. Since Q is countable, we let be the equivalence classes. And we pick PK from QK. Then the Vitali set V. Then is a Vitali set. It is known that the Vitali set isn't measurable, and we won't give a proof here. So, but yet here we need to define another type of non-measurable set. A set is said to be VR if and only if it's a R translation of a Vitali set, where R is also rational. We now also verify the following facts. So firstly, Vs, the intersection between Vs and Vt is empty if S and T are not equal. So again, we use contradiction. We use contradiction again many times per day, huh? Okay, suppose not. Then there exists V1 and V2 such that in V such that V1 plus S equals to V2 plus T. Note that S and T are rational numbers, and then what do we obtain? V1 minus V2 is actually S minus T, which is a rational number. A contradiction arises. Okay, and the second fact is that R is pretty intuitive, that R is the rational translation, union of rational translations of the Vitali set. Okay, since, for any real numbers y could lie on an equivalent class of x. Then we could take something from a Vitali set. That is also in the equivalence class of X. Then all three things are equivalent. The difference between these two is a rational number, and y is in the equivalent class of something, which is a subset of the union. It is easy to verify that these are subsets of R, and hence R equals to that thing. Okay, and hence from the second property we have that again something is something intersection with that something intersecting something that covers it, and then so theoretic manipulation time again of VR equals to A intersect VR. We do know that A is a subset of real and A is non-empty. Then if this is non-empty, then there is something in rational numbers such that this thing, at least one of these things, should be non-empty. If all of them are empty, then A should be empty. Okay, so there is okay is such that A intersect V R K is non V of okay, let's call it RK is non-empty. Okay, so and we now show that such sets are not all measurable. So again, we use contradiction. Now, probably the last time we used contradiction today. Suppose all such sets are measurable. Then the Lebesgue measure of A under similar manipulations with some pretty simple inequalities and let's construct a different set. Since this thing is non-empty and everything inside is irrational, because here in E it's something by Vitali set, and then minus all of them, you'll get something that's different is is irrational. Okay, so since and you note that neighborhood contains both Q and minus Q, right? So if nothing in Q is contained, then this different set contains no neighborhood of the origin. Hence, the E here is not measurable. It is easy to verify that E is a subset of A, and the proof is done.